Lison Blondeau-Patissier, who's going to talk to us about Taylor expansion in games, game semantics.
Thank you. So this is an ongoing work with my PhD supervisors, Pierre, Clairambault, and Lionel, Auclair, about the correspondence between Taylor expansion and game semantics. So obviously you all know about game semantics, right? We have strategies corresponding to programs, and they are usually defined as a set of plays which correspond to a single execution of the program. And the other syntactic side is lambda calculus, in which you have lambda term, usual regular lambda term, and you also have resources, which are kind of a linear approximation of those terms. And so you go from one calculus to the other with the Taylor expansion. I'm going to go back on this later. And what we want to do is interpretation of both lambda calculus and resource lambda calculus that is compatible with that Taylor expansion here. So first I'm going to present more of resource calculus. So usually lambda calculus is defined by the following grammar, where you have a variable x, abstraction lambda x m, and application. And you have an operation called the beta reduction, in which you apply a function to its arguments, basically. So for example, here I take the subterm m, and I replace every occurrence of x with the subterm n. And so if I look at the duplicator lambda x dot xx, I apply it to y, I get 2 copies of y. If I apply it to itself, I get the same thing that I started with. And so I can have an infinite chain of beta reduction. And to avoid this, we can look at another calculus which behaves more linearly. And so it is defined in a very similar way. You also have variable on abstraction, but you also have here application in which the function is applied to a multiset instead of just one single term. So those T1, T2, etc., they are all resource terms, and it's a multiset, so it's not ordered. And when I do this, the beta reduction becomes the following operation. I'm going to match every occurrence of x inside the subterm S with one single resource term of the multiset. And since they are not ordered, I need to choose how I'm matching those two. And so I'm just summing over every possibility, and those are the possible permutations, giving you the match. And so, for example, if I try again to apply the duplicator to itself twice, then I get the following term, and I have a coefficient 2 here because I have actually a choice, because I have 2 x's, but they are matching to the same thing. And if I try to reduce it again, then I get 0, because this time I have still 2 occurrences of x, but I have only one term in my multiset, so I have no matching possible. And so to go from one calculus to the other, there is an operation called Taylor expansion, which is very similar to Taylor expansion with function and derivative. You are approximating a term with its linear approximation. So the interesting part is here what is happening for the application. You look at every possible term which is of the form someone in the Taylor expansion of m, and then a multiset of size n of terms in the Taylor expansion of n, and you sum over all possible n. And so the link between resource term and game semantic is not completely new. There is a paper by Tsukada and Ong published a few years ago about an isomorphism between those resource term and plays. So more precisely, you take resource term in beta normal eta expanded form. So I didn't mention it in the slides earlier, but we are working in a type setting. And type for resource term is exactly the same as a type for usual calculus. And eta expansion simply means that if you have someone which is of an arrow type, so arrow B, then it must start with a lambda x of type A. And so these terms, they are isomorphic to plays in the usual Hyland-Ong game setting, quotiented by a homotopy relation, which I will again explain a bit later. And so we wanted to expand this result with also the introduction of a more dynamic aspect. And so we have an isomorphism that is also compatible with the beta reduction. And to do so, we are not working in Hyland-Ong game setting anymore. We are working in pointer concurrent games, which are a fairly new game model inspired by concurrent name, as the name indicates. And so the main objects are augmentation, which correspond to that idea of play quotiented by homotopy. But first, I'm going to go back on Hyland-Ong games. So you have arenas corresponding to type, and here I'm using the following notation. So an arena is a set of events with polarities minus and plus. So minus is opponent and plus is player. This is coming from a concurrent game. And you have an order, which is an enabling relation. And so since we are interpreting simple types, we only need two things. We need first an arena interpreting base type, so it's the arena O with a single event Q. And then we need the narrow constructor, and we can construct every base type like this. And so each of those Q, they are under the corresponding arena component, and the dotted line indicates the pointer, the enabling relation. And once we have this, we can write play on those arenas. So plays, you probably already know, plays are pointing string. So strings of move of the arena with pointers. And I'm writing them like this. So it's read from top to bottom. Again, each move is placed under its corresponding arena component, and the dotted line indicates the pointer. So the isomorphism tells us that this play here corresponds to this resource term. So the idea behind this isomorphism is that when you have an abstraction, it corresponds to an opponent move. And if you have a variable, it is a player move. And the pointer indicates the link between variable and the corresponding abstraction. So for example, here I have lambda f dot f. So I'm starting with q minus, q plus in the corresponding type. And then in this play, opponent is choosing to first evaluate the second argument of f, that is lambda y dot y. So I am in the second argument part of the type. And then opponent is evaluating the first argument of f. But as I said earlier, plays are not exactly isomorphic. You need to have a quotient. And that is because if you look at this different play, which is different, I mean the events are not occurring in the same order, well, it still corresponds to that resource term, because the only difference is that now opponent is first evaluating the first argument of f, and then the second one. But you get the same thing at the end, and this has to do with the innocent behavior of our calculus, because we are not allowing reference or any interference with what is happening. So the order of the action of opponent should not change what you get at the end. So the homotopy relation is equating those two plays. It is putting into relation plays that can be obtained from one another only by moving around those kind of pair of minus plus opponent. So as long as you move them and you don't break any pointer link, then you find all those plays are equivalent. And so another way to see them is using augmentation in pointer concurrent games. So first I need to define configuration, which are essentially just the states of what is happening during the game, but without any temporal information. So this is just a tree, actually. It's not read from top to bottom or anything. You just have a tree, and still each move is placed under its corresponding arena component. And then you augment this configuration with another order, so another tree structure on top of it, which correspond to the relevant part of the temporal information. So only what player is doing in reaction to what opponent is doing, but we are not ordering here those opponent moves. And this object, which is an augmentation, now corresponds exactly to that resource term that we have here. And you can see that in the first argument of f, you have two elements. So here in that part of the arena, we have two opponent moves corresponding to lambda x dot x and lambda y dot y. And here we have lambda z dot f. So this is the main idea behind the isomorphism. But another interest of using augmentation is that now we want to compose them and to see what is happening if we try to compose augmentation. So let's say I have an augmentation R and an augmentation P. What I want to do is look at what is happening in the shared part of the arena and trying to make these two augmentations talk with each other. So because it is not completely linear in terms of temporal information, we have a choice to make, because we have 2q minus here and we have 2q plus here. So we need to decide which one is going with which one. And so let's say, for example, I take this isomorphism. So I get what is called an interaction, and then, as usual in game semantics, we do the hiding, and we get an augmentation. So this is a composition of P and R, but it is according to phi. And you notice that if I had chosen the other possible isomorphism with crossing arrows here, then I would have gotten a different augmentation because the arrows here would also be crossed, and that would not give us the same object. So the composition really is defined according to the isomorphism we chose. It's not defined in general, which means that if we want to compose augmentation, then we need to define them as a sum and not just a single augmentation. So it is a sum over all possible isomorphism on the shared part of the arena of the composition. If you remember what I said earlier about resource calculus, this is very similar to the definition of substitution in resource calculus, in which we need to sum over all the possible permutation in order to define the substitution. So again, here you have the main idea on why this is also working with the composition. And finally, now that I have a formal sum of augmentation, I can define strategies as formal sum of augmentation with coefficients. And notice that this is exactly the same kind of object as the Taylor expansion, which is defined as a sum of resource term. So putting everything together, we get a category. I don't have time to go into all the categorical details, but you define composition in the quite obvious way. And then you have a category with object as arenas, and morphism, they are just strategies from A to B. And we needed to find the right kind of categorical structure to express what we wanted. So we came up with resource categories, which are a bit inspired by differential categories. But again, I don't have time for this. But what's interesting is that using those categorical properties, we managed to prove first the following isomorphism. So if you take resource term in normal form, and also eta expanded, then it is isomorphic to some augmentation of pointer concurrent games. And this dot here indicates that we are only looking at augmentations that are well open, that have only one initial event. And you can understand that by thinking about the fact that if you have one initial event, then during the composition you can only be used once because you only have one way to be used. So this corresponds to the linear behavior of the substitution. And so we have this nice diagram commuting where you have a resource term, and if you normalize them, you still get the same interpretation. And also using this categorical structure that I didn't have time to talk about, well, if you restrict it to only its comonoid morphism, then you get a Cartesian closed category. And you know that, it is known that if you have a Cartesian closed category, then you can interpret lambda calculus, usual lambda calculus with it. So I wrote work in progress here, but it's mostly done. I mean, most of the proofs are done. It's just not properly written in LaTeX. But so if you take M from the regular lambda calculus, then you have an interpretation given by the fact this is a closed Cartesian category. And if you perform further Taylor expansion and then eventually if you want to, you can normalize it, then the interpretation you get are equal to what you get from the interpretation of the lambda calculus. Okay, so putting everything together, we get this nice diagram which explains why I said that Taylor expansion is game semantic, because, well, it is up to isomorphism. And so I could have mentioned, actually I talk way faster than I expected, so maybe I have time. But I expected not to have time to mention coefficient in pointer concurrent games, because I said that Taylor expansion is defined with coefficient, and I just didn't say anything else about it. But so it also has a meaning in pointer concurrent games, because it has to do with symmetries and the different way in which you can move around your initial event of augmentation. I'm not sure if this is clear. And also, I could have talked about a bit more about what does that mean to only look at comonoid morphism. So what does that mean in terms of game? Which strategies are behaving in this way? Finally, everything here, it's not, maybe it's not clear on that diagram, but everything I just said, it is only in the typed setting, because we need every term to be eta expanded. And so another thing that we are doing is trying to prove the same kind of thing, but in a pure setting, which is a bit technical, because how do you define the eta expansion of a term if it's not typed? And so we have kind of infinitely eta expanded pure calculus, which should be able to give us the same kind of diagram, but in the untyped setting. I think that's all I wanted to say, so thank you.
Other questions? I've got a question, or even a few questions. The first one would be about, so there's this standard result about resource calculus with bump trees, like this kind of connection, and we also know that bump trees and game semantics are really related. Is there a way to see this in this setting, like to factorize the result, the correspondence between Taylor expansion and bump trees, like the fact that they commute? Could we prove it using the kind of connection you have between game semantics and Taylor expansion?
I think this is kind of a bomb tree. I think you could see this object as kind of a bomb tree of this term. So I don't think we have written anything about it, but yeah, it should be quite direct, I think. So.
Okay. Other questions? Otherwise, I will continue to ask some. So. And yeah, I had another question about the differential lambda calculus, which, would it be possible to see like this differential operator as an action on strategies or something like that, since you are targeting the resource calculus? Would it correspond to something in terms of game semantics?
I'm not sure, because I'm not so familiar with the differential lambda calculus, but we know how to construct, almost how to construct this semantic from differential categories. So I guess we could have a link.
Okay.
No question.
Okay, so let's thanks Lison again.